Okay, so I want to talk about this idea. Um, so I've been looking at fantasy consoles for a while now. I think they're really fun, but I have some issues with them, so I took my own time to kind of approach my own style of fantasy consoles. Uh, the name is going to be rattrap for now. It's a very early prototype, but yeah, let's get into the discussion. So these are fantasy consoles. You can see these. They try to get like a very old school feeling on the graphics. Right, they try to kind of fake a very constrained development system. You only get so many pixels per sprite. You only have so many uh, palettes to represent the pixels colors. This is all cool and all, but really deep down, I think these fantasy consoles are still not old school at all. I mean, you look at this code; it's really high level Lua code, and say if your hardware happens to be this low resolution, chances are your CPU is not very fast. And if it's not very fast, it cannot afford too many cycles per frame. Um, so if you're programming a high-level language, that probably means it's going to produce a lot of garbage instructions that just happens because you're kind of programming through like an intermediate language. Um, mostly people don't do that if you're programming on a very constrained system. So this basically breaks the immersion for me. Plus, I have to kind of write code in this very horrible 8-bit style that's really hard to read. So, yeah. So, what really I think is when these virtual consoles claim to be old school, they want to bring back the joy of programming and old times. It's really cosmetic that they try to get in on a really in the essence, they still follow the modern programming paradigm to use high-level APIs to let the programmer communicate with the hardware, which, is still kind of going through like an operating system. The person who uses these APIs have no idea what they get turned into, right? And you also have these high-level languages that gets compiled to instructions that you don't know what they're going to be. Really, I think if you try to have a console that you want people to enjoy programming, you should give them kind of the lowest access to the hardware, including generating instructions by hand. So you basically write an assembly code for your game. And I think this is where a lot of the fantasy consoles kind of fail. They don't really give me the intimacy for the hardware because there's still this really thick layer between me and the console itself. So, so what I think is what really brings joy to me when I do old school game development, when I try to program on the Game Boy, it's really the full control. The programmer has control to the hardware, not the other way around. And there is nothing in between you and hardware. On modern computers, you got the operating system layer in between you and the hardware. It tries to boss you around. It doesn't let you do certain stuff. You require privileges to do certain stuff, and you need to like go through this convoluted API calls to draw a pixel to the screen, which is completely insane. Well, I guess not with the multi-program paradigm, but you get the point. It makes the life of a programmer very sad. And most fantasy consoles, they don't really, follow these philosophies. They still do what the modern computing is trying to do, which is, high-level language for expressiveness. But then you lose the control, the very precise control over hardware, by which I mean, you know exactly how many cycles your code is gonna run at per frame. And the high-level API calls hides the details of the hardware, which kind of blocks the access to the hardware. So in the end, in these fantasy consoles, the constraints that they provide are, okay, you have this little memory, you have this little resolution, but you still have like you still need a very fast CPU to kind of execute a high-level language. So that's kind of funny, which I think it's not working for me. At least some people might enjoy it, but I want something else. But sadly, I don't think there is an option for that currently. in fantasy consoles. So I'm kind of prototyping my own. I'm calling it rattrap. It has a very simple hardware model, as you will see soon. Basically, all you have to do is you write assembly code. The instruction set is very simple, and it's so simple that it's not even expressive enough. There's no intermediate API layer. You do stuff by just writing to the memory, basically. Yeah. So here is the basically the hardware model I'm going with for my virtual console. On the left, you can see it's memory segmentation. Basically, you have a single address space. It's all in a one chunk of memory. The code and data are loaded from disk, which will be different per game, and it will be whatever you author from your tools. The code is basically the instructions that you want the console to be executing. The data will be whatever textures you draw or whatever game save files you have. The work RAM is intended to be general RAM, so it's like allocating memory you can think of. And if you want, the stack can also exist in the work RAM. The video RAM is basically where you draw the pixels. Instead of doing function calls like draw rect, draw circle, on this console you will have full access to kind of communicate with the hardware by literally writing to the video memory. You draw pixels yourself instead of letting the function call do it for you. And lastly, you got the I/O registers, which helps you communicate with the hardware without any intermediate API layers. And on the right, you got the CPU. It's a very traditional execution model. In order to do any kind of computation, you kind of have to load memory from, of course, the memory to the CPU into CPU registers. You do arithmetic with the registers, and you store the result back to the memory. As you can see, you got 16 registers, and the last register is the program counter. It'll be pointing at the instruction that you want to execute next, and you got a status register to store kind of for branching and conditionals. And the video output, the choice is 320 by 240. Pixels are 4 bytes, so you get the precision that you have for a modern monitor, which I think is quite reasonable. One thing is to look pretty, right? And they're laid out in a row major format in video memory. The execution model, the choice here is that instructions are encoded as 32 bits long, fixed size. The reason is so it's very simple and the execution becomes very predictable. The program counter is just going to advance 4 bytes at a time. And because everything is so simplified, there's no layer in between you and the hardware. Doing anything becomes very simple. So rendering, you just have to write to the VRAM. Signaling hardware, just write to the I/O registers. There's no API required for anything. And what's kind of crazy as a result of this is kind of the code can write to itself, so it can be a self-modifying code, which I think is kind of interesting and dangerous. And the core instruction set looks like as the following. You got some arithmetics, you got some bit shifting, bit manipulation, you got store memory in between the main memory and the CPU. You got conditionals and branching. Just things you would expect out of a computer. So besides these, so the hardware, unfortunately, it's not going to be executing your code all the time. The CPU execute your code most of the time until there is hardware interrupt, which will switch the control flow from your code to the interrupt handler that's built into the hardware. The interrupt handler is kind of unavoidable because it needs to take control of the hardware in order to do things like video presentation, input polling, etc. So let's talk about video presentation. It's kind of important, which is kind of the first component of the console implemented for this prototype, because I think rendering is the most important thing in the game. Hardware interrupts, it's triggered on a regular basis. in a deterministic intervals to basically kind of request the programmer to present the current video memory to screen. Of course, this negotiation doesn't always go well. Sometimes the interrupt triggers when the CPU is not ready to draw the frame, or hasn't finished drawing the frame. So there, the interrupt kind of has to give up and falls back to the CPU code. But that means it misses a frame. The CPU also, after it finishes the frame, it needs to wait until the hardware actually takes your frame and blit it to the screen, then you can start drawing to the same buffer. It's kind of a limitation from having a single buffer, which unfortunately is something in the prototype, but it's very open. I'm open to kind of changing this paradigm into like say a double buffer scheme where stalling CPU doesn't really have to happen. Like I said, the synchronization happens. The specific detail is that there's one VBR register in the IO registers. It's the register used to communicate between CPU and a video presentation interrupt. So how it works is that the VBR is set by the CPU to signal the hardware that the frame is ready to be blit to the screen. And once the interrupt handler receives the signal, it draws the video to the screen and clears this bit. So it signals back to the CPU that the frame has been drawn. You can start writing the next frame to the buffer now. So now it forms some kind of communication, and you can avoid screen tearing through this way. There's potentials for frame drops, but you just have to make sure that the CPU always finishes things before the interrupt, which shouldn't be too hard given that you got like a very fine granular instruction set. You can predict the kind of the performance characteristic of everything. And to show this more concretely, I have a demo which we'll be showing now. So here I've got in a demo folder I've got a rattrap, which is the virtual console. If you execute it, it's going to call for the usage pattern, which if you feed it a binary file, it's going to load it as of remember the diagram I showed earlier in the PowerPoint? There was a coded data. So the binary file will be expected to be of that size exactly, and it's going to start executing, treating the first 8 megabytes as if it's code, and the other 16 megabytes as data files. There's also the option that you can feed it an assembly file directly. The rattrap itself comes with an assembler. The issue is then you can't really use any asset because you don't have a your data region in the memory is going to be empty completely. But that's useful for prototyping, say some procedural stuff that you generate data on the fly. So for the demo, I'm thinking we're going to make a XOR texture. The idea is essentially you get, for each pixel on the screen, you have a 2D integer coordinate for each pixel. You take the two components of the coordinate, you XOR them, and use it as the value of the pixel, which can produce some interesting patterns. So just to show you kind of progress, so I will start coding in the rattrap assembly. Alright, so let's see here. I guess the first thing we want to do is to loop over the pixels. So I'm going to use register 1 as the Y component. So here's the label. And here I'll add 1 to, so this is going to be the loop along the Y-axis. It's going to add 1 to the register 1. Each iteration is going to compare R1 with 240, which is the height of the resolution. And if it's not equals to 240, which means the end of the loop, it jumps back to the loop Y label. And in order to loop over all the pixels, it needs to be a nested for loop. So the X component is going to be within the X. Here I'm going to do the same thing. R2 320, which is the width. Then it's not going to go back to the label. So basically we got some kind of nested for loop to iterate over the pixels. Now within each pixel, we're just going to XOR, let's say, intermediate variable R3. First put R1 in it, then XOR R3 with R2. And then, if you remember from the PowerPoint, let's see here, in a hardware model, the VRAM starts at hex 280000. Let's put that in some register as well. R4. Okay, it's 0x280000, which is the address of the beginning of the VRAM. So now we have the value stored in R3. We're going to store R3 to R4, which is the VRAM. Then we remember each pixel is 4 bytes, so we advance the VRAM pointer by 4 into the next pixel, which, if we do this right, it should render the XOR texture on the screen. So, of course, if you just run it, it's not going to give you much. The clock speed is kind of the maximum clock speed. I just keep the CPU running to kind of true away as much instruction as possible. I haven't gotten to lock the clock speed. I haven't determined how fast I want the rattrap CPU to be. So the problem here is that because it's a game, I need some kind of game loop. So I'm basically going to say it's always going to jump back to main. So at least the game is now running. You can stretch the resolutions. But we don't see anything. Well, that's because the problem with video synchronization, you kind of have to tell the hardware that you're ready to, the video RAM is ready to be presented. And that is through the VBR register at the location. It's the first IO register. So it's going to be this address. So at the end of the frame, we're going to remove this. Actually, I'm going to have R5 be store the signal, which is 1, telling them we're ready. And we store R5 into the address. I think that's it. Then after storing signal, frame buffer ready, or video buffer, wait for draw. Then you just keep loading the address. What the CPU here wants to do is it needs to stall, because if we don't stall, we're going to jump back to main and start drawing the next frame, and that's going to override our result. And it's possible for the interrupt to wake up in the middle of that redraw, and it's going to present incomplete. Of course, in our case, it wouldn't, but in an animated rendering, it definitely would have some Turing artifact appear. So it's going to keep. Actually, I can do a label here. So sync load from this address if it's compared with 0. So if the hardware hasn't set it to 0 yet, you jump back to sync. So this is a kind of a signal. This is sync. Let's see what it does now. So now it draws, because the video format is ARGB. Here I am assigning the XOR value directly to the to whatever I'm writing to, and load and store by default is going to be 4 byte wide. I'll be writing at the blue component, but I want it to have an effect on all RGB components. So here I'm going to do something. You can start to see it's kind of annoying to memorize, since if you start using R5, I can't use R5 here, I have to use R6, which calls for kind of the immediate offset, address offset. where I can just set up a stack and x86, you can do something like add say a EX, and you can do ESP4 for the first variable on a stack, and ESP-8, which is very useful. Here we don't have relative addressing, so kind of have to eat the cost of not being expressive. So here we're going to move. So we got an X4 value in R3. We're going to move into R6. I'm going to shift left R3 by 8 into the G component and OR it with R6. Shift left again, OR it with R6 again, and store R6 into R4 instead, which will give us an XOR texture on all components, which will result in a grayscale value. And this is being executed around 300 megahertz, which is the fastest I can get the rattrap CPU to run. Because it's a virtualized CPU, it's not going to run as fast as native due to all the software instruction loading, the instruction decoding. It's going to have a kind of a 10x slowdown there, which is unfortunate. But we want it to be a restrained environment, right? Which is, not as bad as it could be. So here the XOR texture, all it takes, no API calls, no platform API. All you have to do is just 40 lines of assembly instructions, and you can kind of bend the virtual console at your will. Here we wrote an XOR texture, and it shouldn't be too hard to do other effects. Of course, the semantics for the assembly is kind of limited, but that is on the to-do list to be changed to be more expressive. So that is the demo. Here's a disclaimer. What I've shown you and the ideas I've discussed here is just a prototype. It's for just a proof of concept for myself to validate my thoughts on if it's worth pursuing, how it will turn out once I start actually doing the stuff. And so far, it looks pretty promising to me. It's an idea worth pursuing and materializing. So I realize there's a lot of things I still need to add, things like if we had CPU stalling until the frames to be drawing, but that problem, we're essentially wasting cycles. We should be able to start to draw the next frame if we have double buffering. So that will remove the CPU stalling. Also more expressive instructions, like I said, things like relative address or address offset mode, and semantics like call and ret probably set a certain registers to be hardwired for, say, the stack pointer and the base pointer, so that I can have like a function call convention set up for the programmers to follow. Also, there's going to be audio stuff. It's just going to be like video handling, where people are just going to write samples into the sound buffer. That's just going to it's like going to be a ring buffer that the hardware plays over and over again. Things like that. And do be aware that I'm not an expert in designing real hardware. The goal here is really to simplify things down a lot and make it as simple as possible, but still be very powerful in a sense. So yeah, that's kind of discussion I want to have, and here is that's the progress on my fantasy console rattrap. And any feedback is welcome. Thanks for watching.